Hello, chemistry class, and welcome to the very last section that deals with our introductory topics in thermodynamics. Today we're going to look at the quality versus the quantity of energy, and related topics would be energy spread and also matter spread. We're going to look at some ideas about entropy and also energy resources. So let's get started. One of the most important characteristics of energy is that it's always conserved. So if the total energy of the universe will always be what it is now, why are we so concerned about saving energy or conserving our petroleum supply? Let's look at this idea here. If we have some gasoline made up of octane and other similar alkane compounds, and we're burning that, we're producing carbon dioxide, water, and energy. Let's say we decide to take a little road trip. We're going to go from Denver to Chicago. We put that petroleum in our automobile. We make this reaction happen, right? The total quantity of energy doesn't change, but what is happening to the energy? Basically, as we drive along the highway from Denver to Chicago, the energy stored in the bonds of the gasoline and the oxygen is reacting to produce a whole lot of thermal energy that gets spread along the highway, heating the environment, at the road, the air, as we drive our little car along. So in a sense, we can think of it like this. We have concentrated energy in the form of our gasoline. We use that energy to do work, right? To power our little combustion engine in our car. And what we get in the end is spread energy all over the environment. The principle here is really important. When we use energy to do work, and we use our concentrated energy here, we degrade, as we do that work, we degrade its usefulness. In other words, when we use energy, the quality of that energy, the ease of use of that energy is lowered. And we get all this energy and the thermal energy that we spread along the highway to the environment as we traveled from Denver to Chicago. Another idea along this line, I don't know if you've ever heard the term heat death of the universe, but ultimately, if you think of using all of the concentrated energy, at some point, the theory is that all of that would be used and spread evenly throughout all of the universe. And at that point, the universe would be dead. There would no longer be any possibility of doing any work because the energy would be completely spread throughout the universe. Of course, we don't need to worry about this happening anytime in the near future, but we do need to be concerned about how we utilize all of our concentrated energy that we do have available to us, the petroleum, for example. And we'll talk a little bit more about those resources at the end of this video. Let's turn our attention right now to an important concept, and that is energy as a driving force. Energy is a driving force. Let's just consider the example. You're on a camping trip. You're sitting in front of a lovely fireplace watching ashes being produced and energy in the form of heat being produced from your nice little campfire. You would be really surprised to suddenly see the ashes beginning to absorb heat from the air and reconstruct themselves into logs, wouldn't you? It just doesn't happen that way. Let's look at another example of things that just don't happen because energy is a driving force. Let's look at this example right here. Let's say we have a system where we have, these are little ideal gas molecules, okay? Here's our ideal gas molecules. This one has none in them. It's a vacuum. It's empty. We have a stopcock, a little valve right here, and it is separating these two chambers from one another so that all of the gas is trapped in this left-hand chamber. What happens when we open this valve, if we were to remove this valve from the system? Well, we would expect that the gas spreads evenly throughout the entire container. That's what you'd expect, right? We would be very surprised, in fact, to see the following process occur spontaneously. If we had the gas molecules spread evenly throughout both containers, we would not expect this to happen, would we? So let's ask the question, why does this process occur spontaneously from here to here, but the reverse process never occurs? We don't see this going to this. So there are two important forces that are driving these reactions and processes that we've just discussed, as well as many others. And these two important factors are energy spread and matter spread. And let's just talk about those for a minute. Energy spread is referring to the fact that concentrated energy would be widely dispersed. Every time an exothermic reaction happens, energy spread is happening. We get concentrated energy being dispersed. For example, let's just look at burning a candle or burning a Bunsen burner. The energy that is stored either in being burned or being stored in the fuel, the natural gas in the Bunsen burner, is being dispersed into the surrounding air as heat. That heat is being radiated away. It's being dispersed through, radiated is the wrong word for it, it's being dispersed through the air. Whenever we have an exothermic process happening, we have energy spread happening. Energy is flowing into the surroundings through heat. It increases the thermal motions of all the molecules in the surroundings, and that is what is happening, energy spread. I just thought this was really funny because when I Googled energy spread, I pulled this little picture up. I thought it was a great visual to show energy spread. The idea of energy being spread out into the surroundings. It's not really happening in her hair, but it was just a funny visual. Matter spread is the other driving force. In matter spread, it just means exactly what it says. The molecules of a substance are spread out and they occupy a larger volume, just like when we were looking at our two chambers. When we open the little valve, the molecules go from being concentrated on one side into spreading out and occupying a larger volume. When we look at fireworks, we're seeing that matter spread. The particulate matter is being spread across the sky for us, basically, and we see that matter spread happening. Another example of matter spread would be dissolving sugar in water. If you put a sugar cube into a cup of water, it will naturally dissolve, and the matter will spread out in order to occupy a larger volume in that resulting solution. That is matter spread. And that brings us to this really fun idea of entropy. Entropy is designated by the letter S. That is its symbol. And you all know it's basically the natural tendency of components in the universe to become disordered. We see that in energy spread. The fact that the faster random motions of the molecules in their surroundings, that is entropy at work. It is that natural tendency for energy to be spread throughout, faster random motions of them. Matter spread, the components of matter are dispersed. They occupy a larger volume. So we see entropy in matter spread because matter wants to or tends to occupy a larger volume and be spread out and more disordered. Another important idea to remember and keep in mind is that entropy is always increasing. So the entropy of the universe continues to increase as we go on in time. that randomness, that inevitable randomness is always happening, the heat death of the universe, right? But don't worry, it's not going to happen anytime soon, but entropy does always increase. Here's just an example, a little visual here of entropy. If we have gas, it will increase. We'll see that matter spread, and we'll see increase in entropy. You know that entropy is always increasing because, well, look at your room. So that's probably a good example for some of you. Here's a high entropy area. Maybe that should go on. Maybe that should go on the door to my lab. Here, just cleaning goes against entropy in the natural order. These physicists are saying to one another. So, therefore, they're kind of letting their work area look like that. So those are just some funny little pictures to help you get that idea in your mind of entropy. So I said we would get back to this idea of energy, and we have all of these non-renewable energy sources, fossil fuels, petroleum and natural gas. Petroleum is a mixture of a bunch of different hydrocarbons. Hydrocarbons are just molecules that contain only carbon and hydrogen. Here I just wrote down some of those hydrocarbons, some of the names of those. Methane is just one carbon with 4 hydrogens bonded to it. Ethane would be 2 carbons bonded together, and then hydrogen would occupy all the other bonding spots on the carbons. Propane would be 3 carbons, butane 4, pentane 5, and then if we have 6 carbons is where we get hexane. Heptane is 7 carbons, and octane would be C8H18. So those are the hydrocarbons. Petroleum is made up of a bunch of different hydrocarbons, a mixture of that. Natural gas is usually associated with petroleum deposits, and it consists mostly of the methane, but also it has a lot of ethane, propane, and butane in it as well. These are all examples of our concentrated energy that gets, when we use it for work, then it is spread and it is lost to more useful work. It's non-renewable. Here we have some renewable resources, renewable energy resources. Those are, you can look more into these as well if you'd like to for some of your advanced proficiency, see how use is trying to be made of some of these ideas, since they are, as they say, renewable. So one last thing to mention, and you've probably all been very familiar with this through the years of all of your science classes, but the greenhouse effect and how that ends up happening is just an important aspect to consider as well. The Earth's atmosphere is transparent to the visible light from the sun, and that visible light strikes the Earth. Part of it is changed to infrared radiation. That infrared radiation from the Earth's surface is strongly absorbed by carbon dioxide and water and other molecules that are in the atmosphere. And in effect, the atmosphere traps some of that energy, acting like a glass in a greenhouse and keeping the Earth warmer than it otherwise would be. So since the burning of fossil fuels contributes a significant amount of carbon dioxide to the atmosphere, and it's in essence that the temperature of the Earth's surface is controlled a lot by the amount of carbon dioxide and water in the atmosphere, that is something to also be considered as we burn fossil fuels and use them as well. If you would like some advanced proficiency, you could definitely look into Gibbs free energy. It's something we didn't talk about at all, but look, what is that? What am I talking about when I say Gibbs free energy? This is a formula that extremely useful. How can that formula help determine if a reaction occurs spontaneously or not? It's a whole nother topic. It's a great topic. It is how enthalpy, entropy, temperature are all related, and how they can tell us if something's going to happen spontaneously or if it isn't. There are a lot of factors involved in the spontaneity of a reaction and if it occurs. For example, like our ashes and water reconstructing themselves into wood, there's a reason that doesn't happen. So see if you can find out, and I'll see you in class.